Hi, welcome to Unit 5.4. This unit is broken down into 4 parts. This is part 1 of 4, and in this unit we'll be exploring buffers. So you first may be asking yourself, why is it important? Why do we need to study these things? Well, simply put, without buffers, you would die. So what you may not know about your blood is that your blood has to maintain a pH of about 7.4, slightly alkaline, slightly basic, and it has a very small window in which you're okay. So plus or minus 0.05, then you're fine. But if you're outside of that range, then you could potentially die. Your organ systems will start shutting down. And so then you may be thinking to yourself, well, why or how does my body maintain this very small pH window? And it has to do with buffers, specifically buffers that involve carbonic acid, which is shown here, and then its subsequent conjugate bases. So the thing to remember is that buffers, we sort of experience and deal with them all the time. We don't really think about them, but they are a super important part of our life, and without them, there may be no life. So what are buffer solutions? Buffer solutions are solutions that contain a weak conjugate acid base pair, and we'll look into that later. And they're important because whether it's in your blood or whether it's in some other sort of solution, they sort of protect the solution from a drastic change in pH when you add an acid or a base to it. So if you add an acid, for example, you expect the pH to decrease. If you add a base, you expect it to increase. And buffers just make sure that that increase or decrease is not very dramatic, doesn't happen very drastically. Real world examples of this, we've mentioned blood, but also in shampoo. And there are many other examples where there are buffers that sort of maintain that pH of the solution. Okay, so we're mentioning conjugate acids and bases, so let's just quickly remind ourselves what they are. The conjugate acid is the acid form of a base when a base accepts a proton, and a conjugate base is the base form of an acid when that acid donates a proton. So what do we mean by that? If we take something like sodium hydroxide, remember sodium Na is our spectator ion, so we can sort of like ignore that and just focus on the hydroxide part, which would be OH minus. That's our base, and bases accept protons, so it's going to accept a proton from hydrofluoric acid or HF. Okay, so the OH minus accepts that proton and it's going to form water. So water is the conjugate acid of this base because when OH minus gets a proton, it forms water. Now, the reason why that's important is because the water, if it's acting as an acid, it's going to donate a proton, and then that's going to form the OH minus, the hydroxide. And so that's what makes them a conjugate acid base pair. You can go from one to the other by adding or removing a proton. The same thing with the acid, hydrofluoric acid. It has a proton to donate, which will donate to the hydroxide. And when it does that, it's going to form fluoride. Remember, sodium is our spectator ion, so we're just going to focus on the F minus or fluoride part of this, salt. And so this is now the conjugate base of HF. So when an acid donates a proton, it forms its conjugate base. Now, again, this conjugate base, F minus, can accept a proton from, let's say, water, forming the acid again. So they can go back and forth between each other. So and they are in equilibrium if the acid or base is weak. Okay, so let's talk about how do we make a buffer solution. Making a buffer solution involves mixing a weak acid and a weak base and a soluble salt. And when I say soluble salt, what I'm really saying is the conjugate base and acid respectively. A salt of that. So let's take a look at what I mean by that. First off, we should know that a weak acid and a weak base is just basically anything that's not a strong acid or strong base. And on the next slide, you'll see a list of strong acid and strong bases. So if it's not on that list, assume it's weak. Let's take this example right here at the bottom. We have acetic acid, which is a weak acid, mixing with a strong base, lithium hydroxide. All right, pause the video now and see if you can predict the products of this reaction. Great, so what you should have here is lithium acetate and water. Now again, lithium is a spectator ion, so what are the two parts of this that would make a buffer? we have the acetic acid and the salt of that acid, which is the lithium acetate. And why does it make a buffer? Because this is a weak acid, and the CH3COO minus, right, is our conjugate base. Remember, lithium is just a spectator. So we're focusing on the non-metal portion of this salt. So that means if you have two of these together in the solution simultaneously, you have a buffer solution. Let's take a look at the second example. The second example here, we have ammonia, and we should know that technically in water, this should be NH4OH. I was being a little bit lazy here, but when you mix an amine with an acid here, this is hydrobromic acid, so this is a strong acid. When you mix these two together, it's going to form an ammonium salt, right? So which two of these would make the buffer? Great. So NH3, which is your weak base, and it's the salt of that weak base would make a buffer. Once again, NH4 plus is the conjugate acid of NH3, and the Br is just the spectator ion. Okay. So when we say salt, what we're really saying is that they're conjugate of the weak acid or weak base. Now, I just wanted to show you the 6 strong acid and 6 strong bases. This list for bases, I think, can be a little bit bigger because it's essentially all the group 1s except for francium. Any group 1 hydroxide except for francium will be a strong base. So once again, if you're not on this list of strong acid, strong base, you assume it's weak. Okay, now that you have all that information, you're going to answer this first CFU, and this is a select all that apply. So I'm sorry that wasn't written on your packet, but it is a select all that apply. So that means that you're going to pause the video now. When you press play again, I will give you a hint, and then you'll pause it again, and I'll give you the answer. So pause the video now. Okay, so in this problem, you are asked which of the following salts could you mix with a weak acid, sulfurous acid right here, to make a buffer solution. So what you want to think about is, since it's an acid, a weak acid, you want to know what's the conjugate base of that weak acid, and then which salt would match that conjugate base. And then you want to make sure that the salt, which has a spectator ion, that spectator ion will allow that salt to be soluble. It has to be a soluble salt. It cannot be insoluble. All right, so with that hint, you're going to pause the video now again and then try to answer the question. Okay, great. The answer is C. So the conjugate base of sulfurous acid is HSO3 minus, and a salt of that is both answer choice C and D, but it can't be D because D is a mercury salt, which is not soluble, but C is soluble. Another way what we can sort of think about this in terms of making this salt, we make this salt from the weak acid and then a strong base, NaOH. And so if it's made from one strong thing, then you know that it's going to be, the salt should be soluble. So that's like kind of a quick tip, but it doesn't always work. Let's try that for CFU2 now. So you're going to try the same thing. This time you have a weak base triethylamine. Which one's going to make the buffer solution? So the same hint applies. If it's a weak base, figure out the conjugate acid and then figure out which salt from that conjugate acid would be a soluble salt, and then choose that. Great, so the answer here is both A and B. So let's start with B because B is a lot easier to see. Well, you're looking at it and you know that triethylamine, its conjugate acid will be NHC2H53. And so a salt of that would be choice B, and you can make that salt by mixing the triethylamine with hydrochloric acid. Great. On the other hand, remember hydrochloric acid is a strong acid. On the other hand, A which can be made from mixing triethylamine with a weak acid HF, is still a salt that you can use to make the buffer solution, because even though it's a weak acid that you could make it from, because the salt is soluble. Okay, and so this leads me into the two ways that you can make a buffer. So if you're just mixing this salt, a solution of this salt with the solution of the triethylamine, you can make a buffer from it. However, if you're trying to make a buffer by by mixing this base with and having the base in excess and mixing it with some HF, and your HF is your limiting, so that means you would have the base and then the salt left in solution. That would not work. You cannot make a buffer that way. So let me just show you what I mean by that. Okay, so in that example, if we have the triethylamine and we mix it with the salt of its conjugate acid, we mix it together, that would make a nice buffer because we're mixing the two separate solutions separately, or the two separate solutions, we're mixing them together. However, if we were doing something more like a titration where, let's say we have the weak acid HF and then the triethylamine, and we're adding the acid to the triethylamine, and we don't quite get to the equivalence point, meaning that there's still some triethylamine left, plus the salt that we made, that won't work, because when you make a buffer from a titration, you'll see this later, it has to be a strong acid weak base or weak acid strong base. At least one thing has to be strong in order to make a buffer that way. Okay, so if you're a little confused on that, there's this YouTube video that's linked that sort of goes into more about making buffers. Anyway, that's it for part one, where we just learned a little bit about buffers, what they are. So you can stop this video now and then go on to part two. Have a quality day.